Okay. All right, so yes, next paper is a short survey of weak reasoning assistance by Matthew‑today.
Yeah, hey. So as pointed out here, this is a little survey paper. So it turns out HATRA has a survey track that you can do a one-page extended abstract on a bunch of related work that will hopefully be of interest to all of you. Now the talk is 30 minutes. So there's more talk than there is paper. So please do interrupt. I'll try and keep lots of time for discussion here. And when I say there's more talk than paper, there really is. So I might become a little bit opinionated, and I want to make sure that the opinions, don't blame that on any of the authors that I cited. This is my own framing on top of that work. But I do think the opinionated perspectives, the ideas are old, and I'm more curious just to hear this community's take. So please do shout out or during the sort of discussion near the end. Okay, so this is human aspects of types and reasoning assistance. I'm going to focus on the reasoning assistance side, not so much the type side. And I'm specifically interested for this talk in reasoning assistance for mathematicians. Okay, so not thinking about programs, thinking about mathematicians, whether that's hobbyist mathematicians, professional mathematicians, whatever, thinking about algebra analysis, etc. Okay. So, the thing is about weak reasoning assistance, I'm contrasting that to this notion of strong reasoning assistance. Maybe you could think sound reasoning assistance, right? So examples here are, cock and lean, etc., right? And these are really focused on this notion of soundness, right? And by soundness here, I mean if the tool runs, it says there's no errors, then the claim is really true, and there's no doubt in our minds almost about that. And I think a lot of these, traditional reasoning assistants like this tend to think of soundness as a really hard constraint. I mean, cock and lean focus a lot on having a small kernel, and then everything else is optimized around reducing down to that small kernel, which we can be really sure is correct. And they treat that as a hard constraint, and they optimize things like usability, automation, etc., around that constraint. Okay. And what I want to contrast this to, and again, this is very broad strokes, not universally accurate, but in very broad strokes, what I want to contrast this with is sort of this paper many people are probably familiar with, Social Processes and Proofs of Theorems and Programs. And so the idea here is that, tools like cock and lean maybe by default encourage this way of thinking of the goal of math is kind of this low-level logical formalization. I mean, we had some discussion about this at the end of the last talk, where there was this question of, maybe you get into this mindset of it's a game trying to plug things together and so forth. You kind of see this, in that a lot of times, if the proof doesn't work, it just doesn't work, right? There's no notion of there's not a great notion of an incorrect proof that's still interesting or useful. And a lot of times, in motivating these tools, people that it's crazy that, mathematicians have, some proofs they just can't, agree on, right? There's this notion that proof should really be just this easily machine checkable thing. So I think that's sort of what these tools arguably encourage thinking about math as. Whereas I think, another perspective is more about math as a social activity. It's about as a community coming together to sort of slowly refine a collective understanding of these kind of abstract objects. And in that context, formalization is just kind of one useful tool in the toolbox, right? So, you might be saying, hold on, Matthew, we know all that, but when you want to help with the left-hand side here, with this social, understanding, you just kind of have to make a traditional proof assistant, right? You write things down and it's true, and you want to focus on it being sound, right? And that's what you get. And I think this is what I want to push back on against. And I think that, the main argument here is that, I don't think it's new, is that this kind of really sound proof assistance where you're dealing with, I don't know, universe polymorphism, predictive prop and so forth, it's not that easy for, mathematicians to hop onto. And maybe it's there are more points on this time spent versus understanding gain curve than have been well explored. So I think to make this a bit more concrete, we can compare this to the situation for programs and for programmers, which I think brings a little bit of hope to the situation, right? In programming, you've got this really broad spectrum from, on the one side, you could just write down pseudocode for your algorithm or whatever you're trying to do. That gives you no guarantees at all. Or on the very far side, you've got cock proofs, which give you a lot of great guarantees, but it's really hard to do. But for programs, we've got this whole thing in the middle where, you can write executable code and run it, right? Oh, sorry. Was there a microphone supposed to be? hooked up?
Yeah,
Everyone's watching.
My bad.
it's close enough. It's probably been fine, but yeah, good call.
Yeah, thanks for the
My fault.
reminder.
I should have checked that, sorry.
No
Yeah,
worries.
well, I should have as well.
All right, there we
Thanks.
go. Thanks for the reminder. Cool. Yeah, so in programs, we've got all this great stuff, executable code, automated testing, linting, et cetera. It doesn't give us perfect guarantees, but it's better than pseudocode, right? I think 0 to 1 is the sort of name of the game. But in math, for the tools we make for mathematicians, right, they've got natural language. They can write it down in LaTeX. They've got Coq, Lean, et cetera. And then what's sort of in the middle, right? So this question of what's in the middle is kind of what this survey was trying to call out here. And I think a good way to organize all this prior work here is on the one, you've got this spectrum, and you can either go from the left to the middle, or you can go from the right to the middle, right? It's pretty straightforward. You either take an unstructured tool, add some structure, add some soundness, or you take like a totally sound tool and you remove some structure, remove some soundness, right? So clear framework here. Now again, not that every author thinks about it that way, but this is a way to, this is how I'm putting it. Yes?
Yeah, slightly dumb question. On the previous slide,
Yes.
where would you put Daphne? Something like Daphne or Wiley, so the languages that are supposed to be sound, but proofs are completely implicit.
So would this be like SMT solvers where it's, what do you mean by supposed to be sound but implicit?
Well, I mean, if you could line that covering down under something like COP or even interest, you build a proof. And the holder that we saw previously, you construct a proof. Whereas Daphne, you might get the post conditions.
Mm-hmm.
You did ask for interruption.
Yeah, no, this is great.
You give pre and post conditions, and then as Patrick describes, Daphne either says yes or it times out.
Yeah.
Or no.
But
But it says, yeah, I mean, it's sound. It says yes.
It's not sound, actually. The way it's implemented, Coq is very well checked by the developers and whatnot. Daphne is not.
Yeah.
And it does use a backend as SMT solver, but it just generates axioms and assumptions based on its idea of how the Daphne programming language works. And there's no proof that any of that is consistent.
Okay, there's no known unsoundness though.
No, there is.
Okay.
They haven't fixed
Yeah.
They have several bugs, soundness bugs. They haven't fixed yet.
Yeah, I would think about it similar to SMT solvers, I think, in that it's maybe a bit closer to the middle of the spectrum in that, we're really focusing on automation to some extent. And it's going to be expected that there are some bugs in the implementation. We're not really focused on reducing it to this tiny kernel with, like 100 lines of code or whatever that we can be 100% sure about. But I think, yeah, I mean, it's also like a little bit, well, I guess Coq and Lean, you still can kind of, give sort of specifications you want to prove that aren't, all encompassing, but I think that's another nice thing. But yeah, any other thoughts on that topic?
I think they're still aiming for a correct proof, and I'm not sure that's your point.
Issue,
Even in Daphne, it says yes, then
yeah,
maybe you don't trust the tool completely, but still.
Yeah, it
Well,
just tries to do it automatically.
That's not what's fun.
the question, I mean, if this is about what is the workshop called, the experiences of these tools. I mean, the question of whether the tool itself is sound or whether its implementation of a sound body
Mm-hmm.
is to be very different to the user experience, whether the user is explicitly manipulating proof, okay, and has to be aware of what the proof is, versus in Daphne, where users don't have to be explicit about how they're manipulating the proof. And you write your preconditions, you write your post conditions, but you never have to connect that up to the code or whatever it is you're doing. But certainly not explicitly, you can't visualize.
But you can sort of do that with proof assistance. I'm not sure about Coq, but with Isabel, you can just write auto or something, and it will try and solve it, which is basically what Daphne does with SMT. It does it automatically and gives up and asks for some help. And I've found with it, like Daphne, you write a program, whereas Isabel, you write math. But you can do the Daphne style in Isabel easily. And the advantage, of course, is that it's easier to go into more detail when you need to and understand why it's not working. Whereas with Daphne, it just times out.
Yeah. Okay. Yeah. I think these are all great points, and I love the interruptions. Let's yes. I think these are great points, and we can maybe discuss it towards later as we get there. I will want to go through one or two of these examples just so that we get to it. So I think, one example maybe more on the left-hand side coming in, this idea of taking something like LaTeX and adding structure to it, is this structured proofs idea by Leslie Lamport, right? So the idea here is that, and you don't need to read this. This is an example just to get the shape of it. Instead of, you take a LaTeX proof, right, a prose proof, and then you just, enforce that, you have to write it in the structure, write down the claim and then the justification, the claim and the justification, etc. And, these are not machine checked. It's just sort of enforced in the structure of the proof. But still, you can find a lot of proof bugs. All right, this is an example. You take this proof prose from some calculus textbook, and you write it, claim, justification, and then, it turns out in practice, at least Lamport claimed, you may find, well, actually, one of those steps you weren't able to justify it. Right? So, not actually, checking everything, but giving just enough extra structure that helps the user find something. Cool, and there is a LaTeX package that helps you enforce this. Similarly, we've got the great Penrose idea here, which I think in this framing, what I want you to think about is adding structure to TikZ, right? So here it's maybe less directly about checking the correctness of an argument, but more about communicating in the social aspect of math, right? In terms of checking correctness, though, I mean, it does have this cute thing with the optimization approach. So, Penrose is trying, you give it some like domain-specific, description, constraints of what the drawing you want to make is, and then it, makes a nice drawing for you, right? And it does some like optimization stuff instead of just solving, so that if your constraints aren't actually satisfiable, you get like a nice little close diagram that you can kind of intuitively see why it's not satisfiable. So this can kind of help, your reasoning, even if it's not, perfectly correct. And so then the last, the last main example here is QuickChick, which is removing structure from Coq, right? So we heard about property-based testing. And so the idea here is instead of just, actually proving something true, you might want to use a property-based testing tool, just run things through it and make sure that you haven't made any super, obvious mistakes, right? And that's useful to kind of shake out bugs in your proof structure before you get down to proving it. And I'll quickly go through some more like what I think of as more pure examples of this and suggested focus areas, which I think the last one will sort of intersect a bit more with the question about Daphne. And so the first one is sort of what I see as the most pure coming from the left going in is trying to make a tool that can lint LaTeX, right? So we have linters for code and so forth, but what about LaTeX? This has been proposed a couple of times, including by one fairly prominent mathematician here. And the idea is pretty straightforward. Take a LaTeX document, try and parse it, and then look for common mistakes, right? So you might imagine having a bunch of community-sourced linting rules for different domains of math. You might imagine parsing things into a Coq-like form when you can find them and then fuzz them. So someone did that for the NIST like digital library of special functions or whatever. You could imagine users gradually opting in to stronger checking by adding annotations and so forth. And I think this could be really useful for something like avoiding typos in a textbook, right, where you really have control over what you're writing. So this is sort of what I see as the pure going from the left to the right. And then the last major one is going from the right to the left. And so this is sort of proposing maybe we should have, proof assistants that are explicitly focused on being less sound. So tools like SMT solvers, which I assume Daphne is using, do sort of, well, maybe saying focus on being less sound is not right. I think focusing on ergonomics over soundness is a different way of putting it, right? So like SMT solvers, they make mistakes, right? I think as was pointed out, they have bugs. They're huge, like I think CVC5 is something like 300,000 lines of code. But they work most of the time. If there's an issue, they try to fix the bug so that it's more sound. But like it's not what you see in the Coq and Lean world where you really have this clear, trusted kernel. But I think it's also interesting to look at like giving up on soundness in some sense and saying like, what if we community source a bunch of justifications? So I mean, like on the, again, more sound side of things, you could say, why not just be allowed to call out to Mathematica to justify some sort of, symbolic operation. Why does it really have to get lowered to this 1,000-line trusted kernel sort of argument? How much benefit is that bringing to mathematicians? I think, interestingly, Mizar takes a similar approach. I don't know, hopefully people are familiar with the Mizar proof assistant. Okay, Mizar is a cool proof assistant, sort of first-order logic ZFC. I think for the longest time it had one of the largest math libs in it, and they're still going. I don't know, but under the hood they let you sort of opt into these modes where, like, if you want to just do operations with polynomials and whatnot, it will just sort of do them symbolically. I think some option would actually store reals as like floats, which I'm not exactly suggesting, but basically, it was more about like getting proofs to work rather than having this really strong trusted kernel. You could maybe just, this doesn't have to be a new proof assistant. It could be, a community around Coq and Lean and so forth, where people are okay with using SRA, or they have these community source inference rules. But I think, the sort of defaults in community do matter. And maybe when you've got this sort of thing, you can focus more on things like visualization, liveness, fuzzing, etc. Okay, so I think that's all I wanted to get through there, and we can circle back to the Daphne comment if we like, or other topics of discussion and questions. Yeah. Thank you.
So actually, I think that the Daphne point is really important, because there's a sort of folklore in software verification. Most of your bugs get shaken out not by doing pre-spec code, just by writing spec, right? Thinking hard about it. I wonder, is the same thing true with proofs, right? You're not going to, your proof isn't going to have a bug because you accidentally exploited some unsoundness in Z3 or something like that, right? Your proof is going to have a bug because you wrote down the wrong axioms to begin with or something like that. And so I wonder whether there's something similar. What are the actual sources of unsoundness in proofs, and what gives you the most bang for your buck? And do you really need all of the soundness of an LCS style proof or not, right? Just to get 90% of the bugs out of the proof. I don't know, right? I think that's a really interesting question.
Yeah, I mean,
Can you summarize the question for those who are online?
Oh yeah. Well, I guess the question for those that were online was sort of pointing out that for example, Z3 may have a soundness bug, but but it's unlikely that you're going to happen to prove your program correct, because of that unsoundness bug accidentally, right? Like, that's not going to be what makes your proof go through. So I think definitely, like, if the bugs are sort of orthogonal, right? Like if your Z3 has an unsoundness bug because you put a front end to it that says, if tool is coming from, if the input is coming from Daphne, report unsat, right? Like, that's a problem. But if it's some, I mean, I think a way that I think about it, which I would be curious to get people's takes as well, is like I guess like in simply typed in sort of Russell simple types, right? Like maybe you have or is that simple types? Well, I mean, a proof system where you have T is of type T, right? Like, how likely are you actually to get a false proof in the sort of proofs that you would want to write, if that question makes any sense?
It depends on if you're trying to avoid the malicious parties or if you can trust them.
Right.
And it's actually trying to make proof.
And I guess the argument here is that who are the malicious parties, right? I mean, like, mathematicians.
Trying to get his paper approved.
Well, yeah, but compared to submitting a paper in LaTeX, right?
Yeah.
I mean, yeah. So I think this is a really good question of what do we care about? Do we care about adversarial parties, or do we care about sort of helping the mathematician who just wants to come up with a correct proof? And I think this is a question. Yeah.
If I could kind of comment on the Daphne issue, I'm not the most well-versed in Daphne, but at least for SMT solvers, my impression was that in theory they should be sound, so any unsoundness comes from errors in the implementation. I feel like that's a little bit different than saying that they don't care about soundness.
Yeah. No.
Yeah, I think that's the right way to put it.
Yeah, and I'm definitely I'm friends with some of the SMT people. I mean, I definitely agree. I'm not trying to say that they don't care about soundness, but I think in the SMT case, it's definitely, soundness doesn't come for free, and if you want really great automation, like arguably they get in the SMT case, and you want it now, not in 100 years when we write really great when we write really great tactics, right? Like, you may need a lot of code that doesn't reduce down to something that's checkable in the Coq type system. right? So and that comes with bugs. So yeah, I completely agree. They're not going for unsoundness, but I think they are, recognizing that there's a trade-off here.
They're willing to move fast and break things.
Yeah. In a way that I think like Coq and Lean communities are less willing to. Although it's interesting, things like I heard recently GMP is now in the trusted kernel for Lean 4, which is interesting. Yes.
For the argument that you don't have a wrong proof because you're founded on something, so I would say that the more automation you use, the likelier it is that unsoundness gets you, right? These solvers are usually used with a lot of automation. Because then you do group search and you basically have a program that just tries a bunch of stuff, right? And that's where if something unsound says, oh, actually this works, then you're already too convinced to that and you don't even really know about it and you didn't think about these details too much. Whereas when you write a proof step by step, then I would agree that yes, it's really unlikely that suddenly you try something and you get surprised that it actually worked out.
Yeah.
Yes, even if you use tactics in Coq too, Coq has had unsoundnesses too, right? And so if you use tactics to do like really deep research, you might come into a similar thing too.
Yeah, I think it's a great point.
I guess getting on the topic of proof sets, there's another interesting thing that comes up. Like, there's things we can prove, like theorems we can prove just by doing like these giant proof sets. But actual mathematicians usually don't want that. They like some kind of understandable proof that gives insight and can be generalized. So I'm actually, even though I do a lot of computer science, I'm actually in peer math. When I talk to mathematicians, they usually aren't even talking about things like the soundness of the tools they're using. They're interested in writing proofs that can be convincing to their mathematicians. Just having steps written out that can be checked to some extent by computers is nice, but I don't think like these giant proof sets is even what most mathematicians are interested in.
Yeah, and that's where I think sort of the more like the much more lightweight stuff, like just linting or fuzzing and so forth. I wonder how useful that might be for mathematicians. Because
On that point, I think it would be very difficult to implement later because it's very scripty.
Yes.
Things come from because it's very stateful. So maybe there should be another language that compiles the later.
Not only it's also because LaTeX can be very unstructured.
It's unstructured, exactly. So there should be a structured language that compiles the later technique, and that would be much easier to lint and fuzz.
Yeah.
And integrate with other tools.
Yeah, I think the folks I mentioned who tried to do this for sort of the NIST stuff, like their biggest issue, they had to write like papers just on parsing LaTeX. Like it was definitely not
and there's
easy.
so many packages that exploit the unstructuredness.
Yeah.
Can I steal your microphone and run around with it? Just
oh yeah,
help
good
people
call.
online a little bit more.
Oh yeah, I've been forgetting to read these out loud.
Yeah, no, it's fine, but maybe just stay near the
Good
mic
call.
there and.
So a major issue in a lot of what has just been discussed is about automation and about what can be done efficiently. A key difference between Coq and SMT solvers is SMT solvers are trying to be automated and they have to be able to speed things up. And the effort is going into that. Coq is not concerned about that, so they've been able to focus that effort on the small trusted core. Okay. If you're talking about program verification, and I know you said you wanted to talk about mathematics, but a lot of the discussion here is sort of drifting to verification, is what a lot of people here are interested in. If you had started out talking about verification, in your initial spectrum, you would have talked about static analysis.
Sure.
Okay, and the issue that we're touching on here is demonstrated really, really clearly in the area of static analysis, where there are static analysis tools that check all kinds of correctness properties of programs. They are not trying to be sound. They are not trying to be complete. They accept that you can't do this perfectly, and they make that trade-off very explicitly in order to get something that works. And they talk about, how many false positives, how many false negatives, blah, blah, blah. This is just part of the course. This is the reality of that area. And the basic underlying principle is, hey, look, what we're trying to do is make software better. And okay, if full perfect proof is unreachable, there's a lot of other things we can do along the way that help.
Yeah.
And it's this practical trade-off between something that's useful versus, more idealistic ideas about soundness and so on. So, you know, that's just a comment about how some of the things that we've been talking about here actually do apply in the verification area, and just some other examples of how that plays out.
Yeah, I completely agree, and I think these have been some of, in practice, the most successful tools in software checking and so forth are things that don't have this full guarantee, but are much easier for people to use. And I think trying to figure out how can we get that sort of good trade-off in the math area, or at least better than maybe what we have, arguably, is sort of the big question here. That's a great point. Yeah, so I guess there.
I'm kind of curious. It sounds like you might be interested. I can't remember the names of them right now, but there are at least a couple of tools I've seen where they're for people who are writing type systems. So you write down your instance rules and basically like straightforward mathematical notation, and they try to find inconsistencies within your rules. They don't automatically check soundness or anything. It's just like it's basically like a very simple way to describe like, okay, are you doing something stupid here? Like, are you making these common mistakes? It's kind of like lifting your rules.
Oh, cool.
I can send you a link to the repository.
Yeah, that would be great.
But someone talked to me about this over the summer, and I thought, wow, that's like really useful.
Yeah, that would be great to add to this if you remember the name. If anybody else is.
I really like this discussion. The weak reasoning assistance sort of is very tool oriented, like you kind of anchor the discussion in the tool. And you had a few throwaway comments about the community norms, but it seems like mostly what you're actually talking about are community norms, because the tools like Coq and ACTA, they have holes that you could admit lemmas and things like that. The tools already let you kind of reason weakly, but we don't allow ourselves, like I'm imagining myself submitting a POPL paper where I've like admitted lemmas, right? And getting reviewer two's feedback on that.
Yeah.
So it seems like it's really a norm kind of adjustment discussion that we have more so than a tool support kind of discussion.
Yeah, I think it's especially definitely for the sort of starting at soundness and taking it away a little bit. I think it is definitely primarily a community thing. I suspect that like if you go from not just like aiming for soundness, but like we may have bugs along the way, if you go for like actually maybe giving up soundness a little bit, that you might be able to get some more ergonomics into the tool itself, like not making people do polymorphic universes and thinking about this sort of stuff, or universe levels and thinking about this sort of stuff. But yeah, I think primarily like the community aspect is a big aspect, and I think that's exactly right.
Okay, well, we should wrap up soon, but I'll take 2 more comments.
Thank you for your presentation. I've heard previously about some research done on the topic of soundiness, which means relaxing soundness constraints on logical tools, specifically for the purpose of speeding them up rather than making them more casual or user-friendly. Would you say that's related to this line of work, or are they orthogonal directions?
I think they're related in the sense that faster tools are easier to use. I mean, getting liveness is definitely a big thing, but I think otherwise maybe they're orthogonal. I don't really know why you would want speed other than to make it more likely people will use the tool. But in that context, I think it's very related.
All right. Thank you.
Yeah. Thanks for the comments.
You want your tools to actually give an answer.
Exactly. Yeah.
I just want to add on to Cyrus's comments a little bit. So, at least my impression in trying to do mathematics in Coq is part of it is you can admit things, but part of it is that if you're trying to like prove a theorem, you're going to need to bring in all these definitions and etc. And I just don't think like Coq at the end of the day is like a program verification / our community tool, less so a mathematician's tool. So I think kind of the libraries that aren't as mature, but also I think because Coq is based on the calculus of constructions and actual mathematical logic tends to be a bit more impredicative and wish-washy, you end up having to do these things in Coq like go using setoids and these universes of types that I just don't think are really done in mathematics. So I think that's a huge barrier to entry.
Yeah, and I think this really highlights where I think maybe like on the tool level, these are things that if you're okay with, possibly somebody could prove false, especially maybe an automated tool, then maybe you can simplify the tool at a level that goes beyond just the community aspect.
All right, Lindsay, claiming one last comment.
Okay.
I'd like to just wrap up here with a rather provocative and very non-technical question. Well, it's really an observation, but a sort of implied question. You started by talking about that paper by DeMello, Lipton, and Perlis.
Mm-hmm.
And my recollection from the discussion that went on back when that came out, I'm old enough to remember that,
I'm not
was that entire thing was politically motivated, and that what it was actually all about was research funding. And it was driven by some people who were very concerned about the amount of funding that was going into automated verification work, and away from testing work. And there was quite a furore that ensued. And I think there were people who resigned from the ACM, etc., on account of it. I just wondered, reflecting whether there's any relevance to the fact that you use that as your motivation in this work.
I will say I have funding for at least another 2 years, so I'm not interested in funding right now. I like the paper. I don't know what to say. It's a nice paper, and I think it's relevant. But yeah, it's an interesting point, and I'm glad to hear some of the historical background.
I just thought it was an interesting irony.
Yeah.
I only heard about that the last few months myself. Thank you for a set of 3 very provocative talks. I feel like we just had so many questions after each one of them. So, and the earlier session.